In this example, we are given the set H, which is the set of all P in P3, such that P of t is equal to AT squared minus 5AT, where A is an R. In other words, A is just a real number. And then we want to know, is H a subspace of P3? The first thing that someone might think about is P in P3? Well, we're told that it is. This first part here says P is in P3. But over here, it says P of t is AT squared minus 5AT. This is a second degree polynomial. P3 is the vector space of all third degree polynomials. So someone might wonder, is this a trick question? Because this looks like a polynomial in P2, not P3. So let's clarify that first off. So we could think of P3 as the set of all polynomials P such that P of t equals, say, A0 plus A1t plus A2t squared plus A3t cubed, where A sub I, we'll say, is in R. In other words, all of these coefficients, A0, A1, A2, A3, those are just all real numbers. So the question then is, can we write this polynomial in the form of a polynomial that's given in this set P3? So let's see if we can do that. Say P of t equals AT squared minus 5AT, and that has to be equal to A0 plus A1t plus A2t squared plus A3t cubed. So if we simply let A0 equal 0, A1 equal minus 5A, A2 will equal A, and A3 equal 0. Then if we plug these values for the coefficients for the A1, A0 through A3 up in here into this polynomial, we will get this expression. So indeed, P of t is a polynomial in P3. And we can extend this to higher dimensions. So this second degree polynomial is in P2, it's also in P3, it's in P4, P5, or any higher dimension space of polynomials. It's not in P1 because we can't write a second degree polynomial as a first degree polynomial. But it is in P2, it's in P3, it's in P4, etc. Okay, so now let's get to the question of whether H is a subspace of P3. So there's two ways, at least, that we can solve this. A shorter, easier way, and a longer, maybe not more difficult, just a longer way. So we'll do the short way first. And that is to take advantage of a theorem that says that if we can write H as the span of a subset of P3, then H is a subspace of P3. So remember the difference between a subset and a subspace. A subspace is a non-empty subset that is closed under vector addition and scalar multiplication. So not every subset is a subspace. Only subsets that are non-empty have to have something in them, and they have to be closed with respect to vector addition and scalar multiplication. Okay, so if we can write H as the span of some other set, well then H is automatically a subspace by the theorem. So let's see if we can do that. We'll take a look at this polynomial p of t, at squared minus 5at. And notice that there's a factor of a in both terms here, which I can factor out. Call that a times the quantity t squared minus 5t. So any polynomial that's in this set H is a multiple of this polynomial t squared minus 5t. A can be any number, so it's any scalar multiple of t squared minus 5t. Well, the set of all such scalar multiples is the span. So if H is the set of all of those p's, then H is simply the span of the set containing t squared minus 5t. Therefore, H is a subspace of P3. And we're referencing a theorem here, but you don't have to say because of some theorem or by a theorem that says blah, blah, blah. Here we're essentially using the result of the theorem, and that's okay. So I can say H is equal to the span of this set, and this set is clearly a subset of P3. Therefore, H is a subspace of P3. And this set here is a subset of P3. And remember, a subset is just a set that is, you can think of it as contained within a larger set. Actually, it doesn't have to be a larger set. Every set is a subset of itself. But t squared minus 5t is one specific polynomial, and it is in P3, so the set containing that polynomial is a subset of P3. Okay, so that was the short way. The longer way is longer. For some people, though, it may be easier because it's perhaps more straightforward. And what we're going to do here is check closure. This is the standard way to decide if a given subset is a subspace. And the way we're going to do that is we're going to form a linear combination of two polynomials that are in the set H. So we've already got P of t, which is at squared minus 5at. Now a is just a parameter, it could be anything. So here's another polynomial, we'll call it q of t, and I'll say it's bt squared minus 5bt. Notice the 5 has to be the same in both polynomials. But the parameter, I could use any letter I want for the parameter. So one polynomial in H is P, another polynomial in H is Q. So this is not necessary for the solution. This is just sort of commentary here. P and Q are both in H. Okay, so now what I'm going to do is form a linear combination of these two polynomials, say alpha p plus beta q, where alpha and beta are scalars, and see if that linear combination is also in H. If it is, that means H is closed, and therefore H is a subspace. So let's see what we get. So we have alpha times p. Well, that's at squared minus 5at plus beta times q, which is bt squared minus 5bt. Then we just use the definitions of scalar multiplication and vector addition in this vector space in P3. So this is going to be alpha at squared minus, say, 5 alpha a t plus beta b t squared minus 5 beta b t, and maybe skip a little bit of algebra here because we're in college, so we can do algebra. Let's collect the t squared terms and factor out the t squared. So we're going to have alpha a t squared plus beta b t squared, and fix that b. Then we'll do the same for the t terms, and we'll factor out the t, and so we'll say plus t times minus 5 alpha a, and then minus 5 beta b. And then, actually, let's factor out a 5 as well out of the second term we have now. So we'll just copy the first term the way it is. And then we'll say minus 5. So actually, let's make that minus 5. Now we've got alpha a plus beta b t. And if we notice now, I've got alpha a plus beta b here and alpha a plus beta b here. So we could say let c equal alpha a plus beta b. And then we can just replace that expression alpha a plus beta b with a c. So then this would be ct squared minus 5ct. And that's an h. It's in the form of an arbitrary polynomial in h. And how do we know? Well, if we go back up and look at the definition of h, h is the set of all polynomials p that can be written as some arbitrary scalar a times t squared minus 5 times that same scalar a times t. And that's what we have down here. Instead of a, we have c, but the letter doesn't matter. It just represents an arbitrary constant. So the way we would phrase this, if we were writing this, say, on an exam, we would say, so h is closed. What we've just demonstrated here, showing that this polynomial is in h, is that h is closed under scalar multiplication and vector addition, and is therefore a subspace. Of P3.